Of course, we could meet Friday. Would that be better? No. Okay, so we're meeting Thursday. Yes, sir. You can pray for. You want to pray for what? Okay, go ahead, pray. I'll allow it.
Dear God, I thank you for this day, and I especially thank you for calculus. Thank you for gems and ninjas to keep the class interesting, even when we get frustrated to our absolute maximum. Thank you that your love is more than just a scalar, but it is truly constant. And we know that the limit of a constant is so constant, therefore your love is always constant. And please give Dr. Cook wisdom to do this stuff right in your effort. Amen.
This was not a spontaneous prayer. Somebody came in and prayed for a Calc 1 final like a couple years ago, and I forget, they had references to like many different science fiction genres. He actually had it like printed out. He read from the script. It was.
We should do a popcorn prayer for the final.
Okay, so surface integration. So I'm gonna, I could talk to you about the integral with respect to a surface area element. I don't think that's interesting. I'm going to go straight to talking about the integral of a vector field along a surface. So let's just kind of get a heuristic idea of what we're meaning by that. So here's some surface S, right? And you could think about field lines, right? You could think about field lines of some vector field. Right? And you could do the same kind of thing we were doing before, where maybe you could tell here, if I was to ask you where's the magnitude of the vector field greater and where is it smaller on this surface, you could tell me, right? Where is the magnitude of the vector field stronger? It's where the field lines are more tightly bunched, right? So the flux of this vector field F through the surface S, through this little bit of surface, right? In some sense, it should measure the number of field lines that cut through the surface, all right, per what? Now, when we did the flux of a vector field in the plane, we could do per unit arc length, right? So here we want to sort of do the analog of that, but it's going to be with respect to, say, number of field lines per area, right? And how do you, what's the notion of area here? Well, to a good approximation, what you want to do is, have you guys ever seen Teenage Mutant Ninja Turtles? You know what I'm talking about? So let me draw another picture. So what you want to do is kind of think about taking the surface and chopping it into little grids. Now, to be more specific here, I have in mind a parameterization. Let's say, did I use big X or little x or R here? I can't remember. Give me a second. R. I used R. R. So R is going to be a parameterization of the surface, right? So a parameterization of the surface is a mapping from some little subset of the parameter space, which we'll use U and V for parameters, right? So the parameterization takes this little, you could think of it as taking this little rectangle, this domain for the parameters, or it could be some other shape other than rectangles. I'm just drawing it as a rectangle to keep it simple. It could be whatever. The parameter space could look at a lot of different things. The point is it takes this, whatever it is, and it kind of bends and warps it and puts it in 3 dimensions and smears it out over something that we're thinking of as being the surface in question. All right? So specifically, in terms of formulas, to be a little bit more specific, R is actually equal to a function. It's got x, y, and z, and these are all functions of u and v, right? And the notation here, we're calling this space omega. Omega is the parameter space. And in short, the situation, if you don't mind, I'm going to erase this motivating comment. Oops. So basically here I have in mind kind of simple situation. R of omega is equal to the surface. So our surface that I'm talking about is covered by one patch. One parameterization covers the surface. And so my comment about Teenage Mutant Ninja Turtles, what I was talking about is you can kind of think about taking this and making it into a bunch of little kind of tiles, right? Right? You could calculate these the area of each one of these little tiles. Kind of like the shredder, you know? He's got the, you know what I'm talking about? No? All right, yeah. Sorry. I tried to come up with some kind of thing. But the question then is, well, we know, what would these lines be? What is this grid I've drawn up there? Well, remember, that's what the parameterization does. It takes the coordinate, the vertical and horizontal lines, u equals to a constant, or v equals to a constant, and it maps them up to these coordinate curves up here, right? And so if I take a particular point, let's say that one, then this direction might be what? The partial velocity in the, let's just suppose it's kind of like the partial velocity in the v direction, and over here you've got the partial velocity in the u direction. Remember we talked about this before, the normal at that point would be partial r, partial u cross partial r, partial v. Right? That normal would point like this, right? And so what's the area of this little tile? So the area, and I labeled this grid. So like this is the ijth one, all right? Aij. So Aij would be something like the magnitude of partial r, partial u cross partial r, partial v at the edge point, let's say ui, vj, magnitude of that vector times the change in u times the change in v. That gives me the area of that little parallelogram, where change in u and change in v are the amount we're going along the little coordinate curves. All right? Well, if you have a parallelogram, right, then if I want the area of the parallelogram, I can take the vector cross the other vector. But the thing is, to be more, if I want to rescale the vectors so that they line up there, what I'd actually have here would be this vector would be like I think it would be change in, let's see here, change in, goodness gracious, change in u times ru, whereas this one, if I rescale it, this guy up here, so that it's just corresponding to change in v, would be like this vector here. But then I take the cross product of those to get the area, because they don't have to be at right angles, right? So it's just not the product of the magnitude. You take the cross product that picks up on the fact that they could be slanted, and that gives me the area of this little parallelogram. So that's the area of the ijth one, based on the partial velocities being crossed. So actually this just gives me, if I take the sum then, if I basically sum this, excuse me, this is the, well, how to say this? If I integrate, if I take the limit, fine, I'm trying to avoid all this writing, but I guess I have to bite the bullet and do it. Sum I equals 1 to m, sum j equals 1 to n. Curses, I guess I'm talking about the surface area after all. Surface area would be this, right? Actually, that's not the surface area, is it? What is this? This is an approximation at the moment of the surface area. If I want to make it surface area, I need to do something else. I need to take the limit as m and n go to infinity. Then I'll get the surface area. Yeah.
So the term partial r partial u plus partial r partial z equals to vector, right?
Yeah.
What kind of multiplication are you doing there? The use of v sub j?
That's evaluation. That's not multiplication.
Oh.
Good question. So the partial r, partial u, partial r, partial v, that's the normal vector. But it isn't really a normal vector field, right? Because, I've pictured it at one point, but you see there's a different normal vector field at these other points, right? And so what does it look like? Well, that depends on which point you're at, There's a normal vector field. Okay. All right. So anyway, definition, the area, well, to be more specific, surface area of the surface S, so described, would be the double integral over the domain, omega, times the length of partial r, partial u cross partial r, partial v, du dv. Surface area. It's the same, it's kind of an old story. We take the thing, we chop it up into little pieces, use differential calculus to capture the typical ijth region of it, and then we take a finite sum, take the limit as the finite sum goes to infinity. That gives us our approximation becoming an exact thing. That motivates our definition. And there it is. Now that doesn't define flux, though, right? That's just surface area. So now this is important, though. This whole expression right here defines what I call ds, which is the magnitude of partial r, partial u cross partial r, partial v, du dv. This is the so-called scalar surface area element. Let me work an example before I go on, if you don't mind. Let's see here. How about something relatively easy? I don't want to get overwhelmed with the computation at the moment. Let's look at a cylinder. And cylinder radius r, and say height h. What do you want to make its axis? What should the axis of the cylinder be? Student's choice.
X, Z, Y.
Y? So you're saying you want to make this y? You said x, z, and y, so I don't know what to take from that. Do you mean this one's y?
I think compared to that 3D plane, the Y is Z, and that Z becomes that Y.
Again, what would you like to make this, x, y, or z? Z? Okay. I'll take it. So if I make that z, a nice parameterization to use, of course, is the parameters we can use u and v. I'll call them u and v, but really the idea here is u is equal to r and v is equal to theta. Wait a minute. Bad choice. What's the equation to the cylinder? R equals to what? R, right? Sorry, this is a very piratey example. R is a bad choice for parameter because R is fixed. I mean, this is R, little r is equal to big R. That's the equation of the cylinder in cylindrical coordinates. So that's a bad choice for parameter. What I should do is maybe use theta and z. Okay, so with that in mind, I do r cosine theta, which here looks like big R cosine theta, big R sine theta, and z. Wait a minute. You mean to tell me that in order to calculate surface integrals, I'm going to need to be able to parameterize surfaces? Yes, I do mean to say that. It's all coming back. Okay, so, oh man, come on. Really? Good grief. U, V, fine. Now, you don't have to, we're not a slave to u and v. You could use r and theta and z there if you wanted to. That's fine. I'm just trying to use u and v to make the connection with the definition more explicit. So what's goodness gracious, what's r sub u, or the partial derivative in the u direction? It's minus r sine u, r cosine u, 0. And the partial derivative in the v direction is 0, 0, 1. And so what is Ru cross Rv? I'll write it as a determinant. This is the normal at uv, right? So what does that work out to? I look at x hat, I've got r cosine u. I look at y hat, I've got actually just r sine u. You lost a minus there.
Oh, right.
And z hat 0. Now, don't take my word for it. I mean, to quote the last decent president we had, trust but verify. So this dot that is minus sine cosine plus 0. Hey, 0. Woo! And the dot product, of course, with RV, it's perpendicular as well. This is a cross product. We could always check, right? Okay, so what's the magnitude of the normal? It's R. All right, so lo and behold, the scalar surface area element here, ds, is just r du dv, which you might write as r d theta dz, which would be totally unsurprising, right? Because, by the way, geometrically, it really does break down to what you want it to be infinitesimally. Like if you imagine yourself, like a little curvy rectangle on here, and you think about what is the area of a little curvy rectangle on the surface? Well, this width is going to be dz, right? And this, the arc length subtended along the curve, is going to be r d theta. So of course, ds is r d theta dz, right? This definition is just a way of formalizing that. For examples where we can't draw this picture and convince ourselves with resounding intuition that the surface area element is what it is. Oh, and then you integrate, right? I mean, what's the surface area? I mean, so theta goes from 0 to 2 pi, and z goes from 0 to h. We get 2 pi rh. Okay, no surprise there. Okay? Want to work another example? How about a sphere? So here we'll have r of, let's say, well, I'll say phi theta, all right? Radius r. So in spherical coordinates, the equation of the sphere is just rho equals to r, right? Parameterization, r cosine theta, sine phi, r sine theta, sine phi, r cosine phi. We previously worked out that the normal in this case, which is partial r partial phi, crossed with partial r partial theta. Remember we worked this out? Well, I don't know if we did or not. I've worked it out before. Maybe you haven't. I don't know. Anyway, it's totally unsurprising what it is. It's a sphere. What's the normal to a sphere? It's the radially. It's basically rho hat. But it picks up a factor of r squared. So what you end up with is, oh, fine, I'll just calculate it. You guys talk me into it. The determinant of x hat, y hat, z hat. Let's see, your partial r partial phi is r cosine theta, cosine phi, r sine theta, cosine phi, minus r sine phi, theta derivative, minus r sine theta, sine phi, r cosine theta, sine phi, 0. I love that 0.
Wait. Why did you change the... You integrated according to theta, but you also seem to have integrated according to phi.
Yeah, the middle row is the derivative with respect to phi. The red row is the derivative with respect to theta. So what's the normal vector field work out to then? The normal at phi theta is equal to, let's see here, r squared sine squared phi cosine theta, r squared sine squared phi sine theta, r squared sine phi cosine phi, I think. Yep. Now, if you don't believe me, you can easily go back and check that the dot product of that and the second two rows in the mnemonic determinant above, in fact, are 0. There's a sine squared plus cosine squared in the third component, which goes to 1, if you're wondering. Of course, you can do something here, right? You can factor out r squared sine phi, and what you're left with then is this thing, sine phi, well, I'll write it this way, cosine theta, sine phi, sine theta, sine phi, and cosine phi. All of this is what we call rho hat. It's the sphere, it's the unit vector in the direction of increasing spherical radius. Yeah, it is somewhat similar to that. It is familiar, indeed. Okay, so to collect my thoughts again, we have that, let me put it together here. We have, fine. So, I can't decide where to write. What do we get? What's the magnitude of n? It's equal to r squared sine phi. Now, how do I know I don't need absolute value bars there? Remember, phi goes from 0 to pi. Sine is positive on the natural domain of phi, so that's positive. And the scalar surface area element here is just r squared. It's getting in the way. I just want to say that this whole piece here is rho hat. So what I have then is I've got ds is r squared sine phi d phi d theta. That's the scalar surface area element for the sphere. So we can calculate the surface area of a sphere now, right? Integrate from 0 to pi, integrate from 0 to 2 pi of r squared sine phi d phi d theta. Oh, thank you. Yeah. I flipped my bounds. So what happens here? You got 2 pi r squared minus cosine of phi evaluated from 0 to pi, which is what? 4 pi r squared. Yeah, there you go. Surface area of a sphere, 4 pi r squared. Now you know.
Wait, you did number 4?
Oh. Yeah, well, I guess I knew before, but anyway. We discovered it again. Woo! One more example, and then I will promise to stop doing examples. How about z equals to f of xy for x and y in some domain D? In other words, find the surface area of a graph. So, first of all, we got to parameterize the graph, right? How do we parameterize a graph? I suggest we use x and y as parameters, right? So basically, r of xy equals to x, y, f. Does that make sense? What's the normal vector field? Rx cross Ry, which is the determinant of x hat, y hat, z hat. And let's see, Rx is going to give me 1, 0, fx, 0, 1, fy. This gives me minus fx, minus fy, 1. So there's the normal vector field naturally induced from the graph. And so the scalar surface area element, what's the length of n of xy? It's the square root of fx squared plus fy squared plus 1, which then leads me to the so-called scalar surface area element. ds is what? There's the scalar surface area element. And so to calculate the surface area under the graph, or of the graph rather, I should say, it's the double integral over the domain of the square root of fx squared plus fy squared plus 1 times dx dy. And there you have it. I'm going to leave these examples up because I have more to add to them. All right, so that is surface area. Now, to calculate flux, what do we need to do? We need to think about, what if there's a vector field, right? Let me use, well, hopefully this works. Sort of. What haven't I used? Does this one work? Kind of. All right, so suppose we've got some, some kind of vector field coming through here, right? Some field lines. And I want to count the flux of these field lines as they intersect the surface. I want to define that. So what I do is I just figure out, basically I'm going to weight it by surface area, and I just want to pick off the part of the vector field which is what? Normal, right? So definition, the integral of f dot ds vector over the surface S. This is going to be the flux of the vector field through S. It's also known as the surface integral of f through S. And all it is we just take the integral of the dot product with the normal over the surface area element like that. So basically, you just, these guys are the brown arrows or the field lines of f. If the, you need to take the dot, basically the projection of the vector field onto the normal to get the part which is actually cutting through. That's what this just does. This selects the component of the vector field which is actually normal to the surface. And then you weight it by the surface area element. Add those up, that counts the number of lines of the vector field which cut through the surface. Now that seems kind of like a drag, this calculation, right? Because what is n hat? N hat would be n divided by the magnitude of n. So I really don't like to, okay, there are problems where I like to calculate like this if I can do it very geometrically. To give you an example of that, like imagine over here on the sphere I have the vector field f is equal to rho hat. On the whole vector field, the whole sphere, I have this very boring spherically outward pointing unit vector field rho hat. What's the flux of the rho hat vector field through the sphere of radius r? It's just the integral of ds, because n hat is rho hat in this case. Right, so I'm just, So yeah, this is just 4 pi r squared. So there are cases where the direct geometric definition of the flux integral is useful and avoids calculation, all right? If instead of doing what I just did, I actually calculated as I'm about to lay out, I would waste a lot of time. Okay, so here's how to repackage this. This is what? This is really the integral over the, over the domain of the parameterization omega. And that's f of r of uv. And let's see here, this n, well, oh man, I'm sorry, I'm still being too detailed. Too much detail. Let's try this again. integral over S of f dot what? F dot n divided by the magnitude of n, right? Times what? What's ds? Remember what ds is? ds is the magnitude of n times du dv. So I guess I need a little bit of detail, but not too much, okay? Just enough detail. You see what happens? What happens? See what cancels? Yeah, magnitude of n cancels, and we're just left with what? The integral over omega of f, and now I'll put the detail in. That's really f of r of uv dotted with partial r, partial u cross partial r, partial v, du dv. So this, of course, is n, right? And by the way, this is why we define ds vector to be equal to partial r, partial u cross partial r, partial v, du dv. This is the vector infinitesimal area element. It's a vector. And it also has, the magnitude is the ds. So you could also write this as ds times n hat. So given a particular vector field, this last formula I wrote is kind of my go-to for how to calculate things, unless I have some sort of geometric simplification like I just did before I wrote this. This oftentimes is what we can take to actually be the honest to goodness definition of the surface integral. So in order to calculate the surface integral, I mean, this notation is not, I mean, I use this was a definition here, right? This equality was definition, but now we've come full, I mean, this is consistent notation. See this ds, if you look at this, like compare this, right, with that. That's ds, vector. See it? You guys can't see it, you're looking at your notes. This is this, all right? So what is the vector area element for the examples we've gone over today? I'll put it in green. Like here, the ds vector is equal to r d theta dz, and the nicest way for me to write it is r hat. Here, ds vector is r sine phi, r squared sine phi, d phi, d theta, rho hat. That's the nicest way I know to write it. Over here, ds vector is minus fx minus fy, 1 dx dy. All right, let me look at a specific example here. Yep.
What exactly is the difference between ds vector and ds?
ds is a scalar. If you integrate it over the surface, it gives you the surface area. ds vector, if you take the dot product of that with the vector field you're given, and integrate that over the vector field, that gives you the flux of the vector field. Let's see here. Let's look at an example. Vector field f of x, y, z equal to x squared, y, and 3. I want to try to find the flux of this vector field let's say through z equals to x squared plus y squared for 0 less than or equal to xy less than or equal to 1. So basically I'm looking at sort of a square. It's well, the shadow of it would be a square. It's just part of the paraboloid that kind of opens up like a bowl. And I want to, you know, when you calculate flux, it becomes important to say what's the orientation of the surface, right? Is it oriented up? Is it oriented down? What's the situation here? Let's suppose that, you know, the oriented upwards. So basically all that amounts to is that I can use ds vector equals to, now I'm going back to that example because this is a graph, right? So what's the normal to it? Minus fx minus fy 1 dx dy. This 1 here is the you know, that, just to draw a picture of this for a second here, very crudely speaking. I can't draw the real thing, but the normal is pointing upward. I can't draw it down there. Let me just draw it down here. The normal is pointing upward. You can tell that that's the orientation of that parameterization of the graph. We have to orient the surface to calculate the flux, because otherwise you don't have an idea of whether the field lines are going in or out of the surface. All right? Okay, so what's ds here? Minus 2x minus 2y 1. And so basically I just have to calculate the integral of f dot ds over my surface is going to be the integral from 0 to 1, the integral from 0 to 1 of, all right, now, I'm sorry, I forgot to do something else before I wrote this. I'm going to have to squeeze it into red right above there. What am I missing? One other thing to set it up. What is f of r of xy? It's f of x, y, and what's the z? X squared plus y squared, right? What does that look like here? That's what? X squared, y, and 3. So I have to do x squared, y, and 3, and dot product with ds vector, which was minus 2x, minus 2y, and 1 dx dy. All right, so what is that? Minus 2x cubed minus 2y squared plus 3. Now we're back to our happy place. Right? Just plain old garden variety double integral. let's see, integrate over x gives me minus 1/2 minus 2y squared plus 3 dy, which gives me minus 1/2 minus 2/3 plus 3, whatever that is. What's that? (11/6)? I don't know. There you go. So apparently this vector field lines up. It cuts in mostly in the upward direction, going through that bowl. Well, it's not exactly a bowl, right? I mean, this thing, I can't really quite draw it. It's some part of this thing, right? But it's the thing that's above the rectangle, the unit. Well, it's not even that. It's this thing, right? So what we're looking at is something like this kind of like little patch of the paraboloid. Yeah.
I'm probably wrong, but for ds, isn't it negative f of y going to be negative 1? F1. Do the partial y of
The normal, okay, there's two things going on here with the surface integral. The one is the vector field, the other is the surface itself. These are disconnected things. So the setup for ds vector is completely governed by the parameterization for the surface. So it has nothing to do with the big F. The little f is, this is equal to f of xy. I'm referring back to this example over here where I parameterized a graph using the so-called Munch patch, the xy, f of xy. And so it's the derivative of this f with respect to y that gives me the y minus y component of the normal. I think it's okay. Yeah, the graph is what determines the ds, because ds is geometric. Like, ds is this thing. What do the field lines of that vector field look like? Well, that's actually a separate issue. But this calculation we did tells you how many of the field lines of this vector field actually cut through that surface, even though I would have a lot of trouble actually drawing it. So in the notes, right, guys, we have a few orders of business to go over. One, I should talk to you a little bit about why this is a good definition, right? I'm trying to define something geometric. This notion of the number of field lines that cuts through the surface, it surely should be independent of our choice of parameterization to describe the surface. The surface is geometric. This parameterization is just a picture of it, right? But there's many other pictures you could take. And so we're obliged to show that this definition is independent of my choice of parameterization. So I owe you an explanation there. What if I chose a different parameterization? How do I know I get the same value here, right? It turns out, as I'll show you in a little bit, it's just the change of variables theorem that does it for you. It's kind of interesting how that goes. That's one thing we have to do. The other thing, of course, is I want to kind of finish this list of standard examples. There are, I think, maybe about five standard examples I like to bounce off of. Cylinder, sphere, graph. Another standard example I like to sometimes use is the cone. These are all great surfaces. Now, the point of making this list of standard examples is, you see, the thing here that's really a drag is the calculation of S vector, right? So here's the rule. If your problem is about one of the standard examples, you're allowed to use the notes to quote what ds vector is and to use it logically. However, if the homework problem is about something that's not one of the standard examples, then you kind of got to calculate from scratch. That's just how the story goes. All right. So I've done about 60% of the work for the standard examples today already. We've got the surface area element, the vector surface area element for the cylinder, for the sphere, for the graph over there. Let me work one more example by hand before I get the projector out here. Let's calculate the flux. So here's a vector field F. Of x, y, z equal to, I don't know, how about 1 over x squared plus y squared plus z squared to the 3/2 power times x, y, z. You guys calculated the curl and divergence of that in the homework you just turned in. You showed it was 0, right? Let's calculate the flux of this vector field through a sphere of radius r. The convention, guys, if your surface is closed, the convention is that we give it an outward pointing normal. That's the positive orientation for the sphere. That thing I wrote over here is the positive orientation. I mean, the choice of a normal vector field is an orientation, all right? Orientation just says which way's up. So this positively orients the sphere. So if we want to calculate the flux of this vector field through the sphere, let me call it S sub r for the sphere of radius r. There's a right way and a wrong way to do this calculation, right? What would a wrong way be? Cartesian. Well, actually, to stick with the Cartesian and to actually plug x equals to r cosine theta sine phi, x equals to y equals r sine phi, sine theta sine phi, r equals to cosine phi into the formula for x squared, y squared, z squared, right? I mean, you could do that, but you really shouldn't, because it's much better to just simply recognize what we're looking at, which is the integral over the sphere of radius r. What is f? F written in spherical coordinates is exactly rho hat over rho squared. Okay, so I'm going to use that. Now you can see it, right? This is precisely rho hat. It's a unit vector that points in the direction of increasing spherical radius, written in x, y, z coordinates. And the other thing is just 1 over rho squared. So f is precisely rho hat over rho squared dot with, ds, let's say, okay? Okay, but what is that? It's the integral from, 0 to pi. It's the integral from, well, just let me, details that I don't need to write. Okay, so integral over the sphere again. What is this on the sphere? What's rho equal to on the sphere? Yeah, rho hat over r squared. What is ds? ds is r squared sine phi, right? D phi d theta. All times rho hat, right? So you see what this, the r squareds cancel, right? And we're just left with the integral from 0 to pi, integral from 0 to 2 pi of sine phi d theta d theta d phi, which is 4 pi. Independent of the radius, right? The radius could be 2, the radius could be 2 million. The flux is still 4 pi. This is an example of what's known as Gauss's law in electrostatics. In 3 dimensions, the Coulomb field is rho hat divided by rho squared. This is the inverse reciprocal field. Its field strength is reciprocal to the distance squared from the origin, and it points in the spherically radial direction. This calculation shows you that the flux of the Coulomb field is invariant. No matter how far out you go, the flux is still 4 pi. Now it gets spread out over larger and larger spheres, which is why the field strength weakens. Nevertheless, the flux is always 4 pi. It's like indestructible. Oh, don't look at that. I'm sorry, I'm showing you a grade book from 126. That's not good. Not that it's especially exciting, but you know, I try to maintain some semblance of professionalism at times. Let's see here. Where are I? Come on, where'd you go? Oh, there it is. Where'd it go? There it was. All right, so I'll go through this rather quickly because it's not, you know, I want you to know this is here. If you get interested in this question, you can look back over this more seriously. But I think logically it's important. So here what I do is I look at the question of, all right, so suppose you had a different parameterization, big X, and it had parameters A and B. Then you can relate, you know, the two parameterizations would be related in the sense that R of u v would be equal to X of H of u v comma G of u v. In other words, you could think of H is equal to A, G is equal to B. So H is a reparameterization. It changes the u v parameters to AB parameters, all right? Just in the same sense we talked about reparameterizations of curves, you could talk about a reparameterization of a surface. You calculate these lovely partial derivatives by the chain rule. They're related. The x derivatives and the r derivatives are related in this way. And then if I put it all together, I have this big chain rule, which is that partial r partial u is partial x partial a times partial h partial u plus partial x partial b partial g partial u, which makes sense. X has a and b as variables. And this expresses how the change in u for r relates to the change in a and b for x as weighted by the reparameterization h. Likewise, for partial r partial v, you find something similar. When you calculate the cross product, so the normal vector field, with respect to the uv coordinates, you get this. Now, if you rewrite that then in terms of the AB coordinates, the AB parameters, you end up with a cross product, again, of the other parameterization times this thing. Well, this thing